Okay, welcome everyone to this Drug Discovery World webinar entitled Real-Time Profiling of Receptor Pharmacology. As we know, receptor function is multifaceted, and it is therefore highly advantageous to monitor multiple aspects in live cells and in real time. This includes ligand binding, secondary messenger coupling, and recruitment of scaffolding proteins such as arrestins, internalizations, and trafficking. So today's webinar will detail the latest advances in microplate reader-based technology to monitor receptor pharmacology, particularly using bioluminescence resonance energy transfer, obviously in short BRET. So today we're delighted to have a panel of three experts to discuss this topic in greater depth. So let's meet them. First up, we have Dr. Thomas McLeight from Promega. Secondly, and all the way from Australia, we have Associate Professor Kevin Flager. And last but not least, Carl Peters from BMG LabTech. I'm Robert Jordan, Publisher and Editor-in-Chief of Drug Discovery World, DDW, and I'm going to serve as your moderator. At any time during the webinar, you can send in your questions for our panelists by writing your questions in the Ask a Question box and obviously pressing OK. The panel will try and answer as many of your questions as time permits at the end of the presentations. Okay, so I think we're ready to go. So if you're all sitting comfortably at your screens, let's get started. Our first speaker is Dr. Thomas McLeight. So if you're ready, Thomas, the floor is yours.
Hello, my name is Thomas McLeight. I'm a senior scientist at the Promega Corporation, and I work for the Advanced Technologies Group. Today I will start this presentation with an overview over BRET and nano-BRET technology specifically. There can't be any doubt about the importance of protein-protein interaction. They are critical to all physiological processes. From a drug discovery perspective, there are potentially hundreds of thousands of constitutive and dynamic protein-protein interaction which provide a rich source, target source for therapeutic intervention and modification of biological processes. Yet, the protein-protein interaction-based drug discovery remains somewhat challenging, most importantly due to the limited number of scalable assays for protein-protein interaction and the lack of chemical space specific for targeting protein-protein interaction. Now, the next slide shows a quick overview over the technology landscape for protein-protein interaction analysis. These methods can be split roughly into two areas. The first one consists of biological or biophysical methods that allow in vitro analysis and endpoint analysis of protein-protein interaction. The second set comprises of methods that allow the measurement of dynamic protein-protein interaction. Despite the relative wealth of methods, most methods are currently limited by their ability to use them in screening environment, by their sensitivity, by their dynamic range, specificity, robustness, and physiological relevance, as well as the ability to conduct real-time analysis. Now, one of the methods that is commonly used is resonance energy transfer. So how does resonance energy transfer, in particular bioluminescence resonance energy transfer, work? BRET is one of the many variants of resonance energy transfer, which is the radiation-less transfer of energy between two lumiophores. In the case of bioluminescence resonance energy transfer, or BRET, the lumiophore comprises of a luciferase as a donor and a fluorescent molecule as an acceptor. Now, the efficiency of resonance energy transfer is determined by three principal parameters. First, spectral overlap between the donor emission acceptor excitation, which is shown in the spectrum shown here on the slide. This is a spectrum of nanolac and Oregon green as an example for a donor acceptor pair. You can clearly see the spectral overlap between the nanolac emission and Oregon green excitation as the orange-colored area. The second parameter is the spatial positioning and orientation of donor and acceptor relative to each other. And lastly, and most important, is the distance between the donor and the acceptor. One important constant in that regard is the R0 value, which is the distance at which resonance energy transfer occurs with 50% efficiency. This distance varies depending on the specific donor-acceptor pair between 3 and 8 nanometers. Equally important is the fact that resonance energy transfer efficiency is inversely proportional to the 6th power of distance. Consequently, even small changes in distance will translate into major changes in BRET efficiency. The scale at which BRET occurs and its exquisite sensitivity to changes in distance make BRET very well suited to measure interactions between macromolecules. Measuring BRET is rather simple. All that is needed is an instrument that is capable of measuring luminescence in 2 channels, one for donor emission, which is here depicted in blue, and one for acceptor emission, which is depicted in red. The sample spectra provide an example how signal changes in the presence or absence of an acceptor are measured. In the absence of an acceptor, you get a large signal in the donor channel and a small signal in the acceptor channel. Please note that the signal in the acceptor channel originates from spectral bleed-through of the donor into the acceptor channel and should be considered background. The amount of donor background is dependent on the spectral separation between donor and acceptor and will ultimately determine the dynamic range of a BRET system. In simple terms, BRET systems with poor spectral resolution suffer from limited dynamic range. Now, in the presence of the acceptor, you still retain a portion of the donor signal. Also, this plot shows spectra normalized for donor emission, but in reality, the donor signal would decline somewhat. But now, with energy transfer occurring, you get a substantial increase of signal in the acceptor channel. This change can be easily captured by calculating the ratio of the acceptor signal over donor signal. Any increase of acceptor signal relative to donor signal would result in an increase of the BRET ratio. Also, the ratio of the raw emission values are frequently referred to as BRET ratio, which is not entirely correct since it includes the spectral bleed-through from the donor into the acceptor channel. Now, to obtain the true or corrected BRET ratio, you have to subtract the ratio obtained from the donor control in complete absence of an acceptor from the ratio you measured in your actual sample. Now, why is BRET so suitable for measuring protein-protein interaction? We can answer that question by comparison to other methods. First of all, it allows real-time measurement in living cells. That can be achieved with other methods such as mass spectrometry pull-down, SPR, or time-resolved FRET. The second reason is that ratiometric assay formats in general mitigate input variation, for instance, due to varying cell number, etc. Other intensity-based assays don't provide this type of correction. An example for that would be protein fragment complementation assays. As pointed out before, BRET is extremely sensitive towards changes in distance. Other methods such as mass spec and pull-down don't really give you any information about distances or if 2 proteins directly interact. It could be purely incidental that you get signals. There is no physical interaction between donor and acceptor. That goes back to protein fragmentation complementation assays, which require actually a complementation of your reporter. That complementation itself can add to the dynamic interaction of the pair of interest. Now, BRET has been around for quite some time. There are a number of known BRET systems. The probably most commonly used are BRET1 and BRET2. Now, BRET1 combines renilla luciferase with YFP. It gives you, in general, good resonance energy transfer efficiency due to the spectral proximity of both donor and acceptor. However, as I pointed out before, because both donor and acceptor spectrally so close together, it gives you very high spectral bleed-through. It is also due to the relative weakness of renilla luciferase, gives you only intermediate to low signal strength and stability. Now, that system provides you with intermediate sensitivity but very limited dynamic range. A second system was developed, it's called BRET2, that combines renilla with a particular substrate, solantrosine HH. That substrate shifts the emission of renilla luciferase to 400 nanometers. That is combined with GFP2, which has an excitation maximum around 400 nanometers and an emission of 550 nanometers. It gives you intermediate resonance energy transfer. Now you have a great spectral separation between the donor and the acceptor, so you get very little spectral bleed-through. But due to the properties of the substrate, you get very poor signal strength and stability, meaning that your signal decays rapidly. Now you get very limited sensitivity with the system, but good dynamic range. So we thought that Promega's technology would allow to improve the BRET technology, and we took a two-pronged strategy to achieve that. First of all, we replaced vanilla luciferase with a new luciferase called nanoluc. Nanoluc is extremely bright. The graph below shows you that it is 130 times brighter than vanilla luciferase and at least 30 times brighter even than modified, improved version of vanilla luciferase such as RLUC8. It has glow kinetics, so it emits a stable signal. It is also very small. It's about half the size of vanilla luciferase, so it is less likely to interfere with protein function as in fusion. It has extremely high physical stability and is very adaptable to different assay formats. On the acceptor side, we changed the paradigm of using fluorescent proteins completely, and we used a second Promega technology to introduce an acceptor, and we used for that halotag technology. Now, halotag is a modified bacterial dehalogenase that undergoes a suicide reaction with a chloralkane. That chloralkane can be substituted with all kinds of chemical payloads, and of course, in this case, we used a fluorophore as a payload. We developed a ligand called nanobret 618 halotag ligand, which is spectrally very well resolved from nanoluc, which gives us great dynamic range. Now, the brightness of nanoluc allows us that we sacrifice some of the spectral overlap and some of the resonance energy transfer efficiency in order to achieve that spectral separation. To give you one example of nanobret versus BRET1 in regard to dynamic range, we tested it in a very well-defined system using FKBP and FRB. FKBP is a small immunophilin. FRB is a portion of the mTOR kinase which binds to rapamycin. Upon binding of rapamycin, FRB and FKBP associated very tightly in a trimeric complex. This particular system has been used to assess the performance of a lot of systems that are intended to measure protein-protein interaction. So we compared it by creating a set of fusing FKBP to the acceptor, which is halotag or YFP respectively, or FRB to nanoluc, to the donor nanoluc and RLUC. And then we basically measured the change in BRET ratio upon addition of a dose response of rapamycin. And as you can see in this dose response experiment, by converting the BRET ratios to signal to background ratios relative to the untreated sample, you get a much bigger increase with the nanobret system compared to the BRET1 system, and substantially increased dynamic range. Now, we have extensively published on this technology, can be found in a recently published paper in ACS Chemical Biology, and of course on our website we have extensive information about the nanobret system and lots of different application examples. Now, nanobret, the workflow for nanobret technology as a protein-protein interaction assay is fairly simple. It starts with the generation of different expression constructs. I want to stress here that due to the requirements for spatial orientation of donor and acceptor, all combinations of donor and acceptor fusions need to be tested. Then you transiently transfect the donor and acceptor constructs. You transfer the cells into the desired plate format. You also treat the cells or add to the cells the nanobret 618 ligand at a concentration of 250 nanomole. You incubate for a brief period of time and then induce your protein-protein interaction if it's a dynamic interaction and it needs an inducer. After the desired incubation time, you add a 5-fold nanoglow nanobread reagent, and 5x nanoglow nanobread reagent, and then measure the emission at 460 and 610 nanometer respectively. Now, the use of an organic fluorophore as an acceptor provides a lot of opportunities that go beyond measuring simple protein-protein interaction. We can use that organic fluorophore to label antibodies. We can use it, of course, to label proteins directly. We can use it to label proteins through halotech, but we can also use it to label small molecules. And it allows you to develop a very broad platform in which not only protein-protein interaction, but any type of protein-ligand interaction can be measured. And to illustrate that point, I show you here an example for the EGFR receptor. So imagine you fuse EGFR receptor at the C-terminus to nanolug. Now, if you combine it, for instance, want to measure the interaction of EGFR receptor with one of its adapter protein, in that case, you would fuse an adapter protein such as GRAB2 to halotag. And then upon activation of EGFR, you can measure the binding of GRAB2 to the EGFR via BRET. However, you could also look at phosphorylation events by using a phosphor-specific antibody. In this case, you would label the phosphor-specific antibody or a secondary antibody with the nanobread 618 ligand. And then basically upon stimulation of EGFR, you have to lyse the cells, add your antibody, and you can measure phosphorylation by adding the labeled phosphor-specific antibody in a fully homogeneous format. Lastly, you can develop target engagement assay for small molecule binders. And here, for instance, let's say you develop small molecule binder and kinase inhibitor against EGFR. You amend it with the fluorophore. Now you can directly measure the binding of a small molecule towards EGFR, the kinase portion of EGFR. Lastly, you could, of course, also label the N-terminus of EGFR with nanolug. That would allow you to measure directly the binding of EGF to EGFR by creating a fluorophore-labeled EGF. And then upon addition of EGF to your EGFR-expressing cells, you could measure the binding of EGF to the nanolug EGFR fusion by looking at the BRET ratio. This concludes my part of the presentation, and I will hand it over now to the next presenter. He will tell you a little more detail about how this technology can be applied. Thank you very much.
Thank you, Thomas, and welcome. So I'd like to talk today about real-time profiling of receptor pharmacology. My name is Associate Professor Kevin Flager. I'm Head of Molecular Endocrinology and Pharmacology at the Harry Perkins Institute of Medical Research in Perth and also the University of West Australia. And I'm also Chief Scientific Advisor of Dimerix Limited. I'd like to start off by just acknowledging a few disclosures. And it's very pertinent to this talk because a lot of this work has been done in close collaboration with the University of Nottingham, Promega, BMG Labtech, and more recently with the University of Queensland and Dimerix. And I'm, as I mentioned, Chief Scientific Advisor of Dimerix and a shareholder as a consequence. I'm going to talk you through various aspects of molecular pharmacology profiling, in no particular order, but binding, coupling to G proteins, recruitment of arrestins, internalization, trafficking, recycling, and heteromerization. All of these are able to be carried out using the BRET technology. So what is BRET? Bioluminescence resonance energy transfer. It's a process where we can label a protein of interest, such as a receptor, with a luciferase molecule. This is a donor for the BRET technology. We can then label an acceptor onto an interacting protein of interest. So this acceptor is generally a fluorescent protein, but can actually be another fluorophore as well. The concept is that as a ligand binds to our protein of interest, such as a receptor, you get recruitment of the arrestin molecule up and interacting, and that brings the donor and acceptor into very close proximity. If that happens, you now have resonance energy transfer occurring. This is non-radiative, and it only happens if these two molecules are in very close proximity, within about 5 to 10 nanometers. That means that energy transfer then occurs, and we get a longer wavelength light emission, so more in the yellow or even through to the red, depending on the fluorophore we use. This means that when we see that light at that longer wavelength, we're seeing this energy transfer, and therefore we're seeing a protein-protein interaction, as was nicely described by Thomas a moment ago. The great advantage of bioluminescence hereditary transfer is that we can do it in live cells in real time, and we can do that by using a luminometer, and in particular we use BMG instruments such as the Clariostar and the Ferrostar, and you can use fusion proteins, cDNAs, generate your donor acceptor cDNA constructs, transfect cells, put them into a 96-well plate or even a 384 or higher, put them into a luminometer, and then measure light through different wavelength channels. So with filtered light, we measure through the blue or the yellow, or it could be red or longer. And we're actually looking to measure and generate a ratio, as again was described by Thomas a moment ago. What I'd like to do now is take you through a few examples where we're actually using the BRET technology to profile in real time in live cells and actually understand some different aspects of what's happening in the cell. So I'll start with profiling clinical mutations in vasopressin 2 receptors. Here we're looking at V2R mutations, and these are some of the examples we focused on. Some of them cause a loss of function disease condition, so we have nephrogenic diabetes insipidus, or NDI. This is loss of function, and it occurs with these mutations R137H, R181C, and M311V. There's also a gain of function disorder, which is NSIAD, or NSIAD, which is nephrogenic syndrome of inappropriate antidiuresis. And again, this happens at the R position, but this time with R137C or L. And also more recently, we've published with the R312S mutation. We've also characterized a mutation or a polymorphism at V266A, and this is associated with patients or a patient with NSIAD, but we actually think this is probably not disease-causing. So to show you some of the pharmacology, here's a publication in molecular endocrinology, and this is showing real-time BRET analysis using arrestin recruitment to the V2R receptor. So here we're looking at real-time, we're adding antagonist, and we're seeing a reduction in the ligand-induced BRET signal. On the first panel here in A, we're seeing the wild-type receptor. In B, we're seeing the C mutation. In C, we're seeing the L mutation, and then D, the H mutation. And you can see there's this constitutive recruitment of arrestin in each case. And this is also reflected on the right-hand side in the confocal microscopy. Now you can always look at this in real time, and this is the beauty of BRET, because you can actually generate kinetic profiles, and you can see this at the different concentrations. The wild-type profile on the left, and then coming across the screen we have the R181C, where we have this complete loss of arrestin interaction. We have this polymorphism, which looks very similar to wild-type, and then interestingly we have the M311V mutation, which gives us this different kinetic profile, and that actually has an intermediate phenotype in the patients. Here we have some follow-up in terms of cytokine-P, inositol phosphate, and arrestin. And again, the Clariostar is an instrument of choice for us doing these TR-FRET-based assays. And here we can actually see the cytokine-P shift in the potency. And that is different for inositol phosphate. And arrestin gives a similar profile, in fact, to the inositol phosphate profile. And this arrestin is with the BRET. So here we can see a different profile for the different endpoints. And you can actually see the V266A is similar to wild type, the M311V is intermediate, and then the R181C still has a maximum cytokine P response, but is right shifted. In contrast with the inositol phosphate and the arrestin, the R181C, we're completely losing that signal. So now if we look at the L312S mutation, here we're looking at a comparison between the R-Leucate Venus combination, the nanoleuc Venus combination, and the nanoleuc halotag combination. And the halotag here we have a red fluorophore attached to it. And you can see that we have similar pharmacology regardless of which system we use. But interestingly, we have a very clear constitutive signal with the R-Leucate and Venus and the nanoleuc halotag. Not quite so obvious constitutive signal, although it is there for the nanoleuc Venus combination. So now we can look at that in terms of kinetics. Here we can see the different doses going across the screen for the R-Leucate Venus, nanoleuc Venus, and nanoleuc halotag. And we can see here, if we compare that down the bottom with the C mutation, we can see this constitutive signal again. And then as we flick through to the next one, you can see the L also again has this constitutive signal. And then finally, if we look at the combination with the S, we can see that constitutive signal is no longer there. But we have similar kinetics across, regardless of which particular combination of donor receptor we use. So the reason we have this mutation causing the phenotype, it's all about cytokine P, and that's shown here. We have the L312S giving us this constitutive cytokine P signal. We don't see a constitutive inositol phosphate signal, and the cytokine P, as you can see here down the bottom, we have this constitutive signal with the black bar raised with the mutation, and then we have this reduction with the tolvaptan inverse agonist. Now moving towards trafficking, here we have a combination of KRAS attached to a fluorophore, and this time Venus, and we have our receptor on the plasma membrane attached to a donor, this time R-Leucate. So this is a situation that was published first by Nevin Lambert, and the idea is that you can actually have the proximity assessed through the non-specific interaction or the non-specific proximity of the BRET. So the KRAS is effectively lining the plasma membrane like a little minefield, and there's enough of it that regardless of where the receptor is with the donor, it will be proximal to a KRAS and therefore give a signal, whereas when that receptor comes off the membrane, it goes into another compartment, comes away from the KRAS, you lose that signal. Now we've kindly been given constructs by Nevin and used some of those, and we've also expanded that portfolio to now cover a whole different range of compartments. So we have RAB5 and RAB4 in the early endosome, which is the compartment that has the EEA1 marker. We have RAB11 in the recycling endosomes, which is the marked by transferrin. We have late endosomes with RAB7 and RAB9, which is marked by lysotracker, as is the lysosome with RAB7. And then across here we have RAB1 in the endoplasmic reticulum, and then cis Golgi marked by the GM130 marker, where RAB6 is located, and then we have RAB8 in the trans-Golgi network. And to show that those are correctly located, here we have a flag-tagged V2R showing co-localization with the KRAS Venus, and the merging there showing it nicely co-located on the membrane, the plasma membrane. And then to validate the other compartments, we have the early endosome marked with the EEA1 marker with the RAB4 and the RAB5. We have the RAB1 with the GM130 marker, so that's in the Golgi. And the RAB8 is not co-located with the GM130 because if we consider the previous figure, the RAB8 is actually located in the trans-Golgi network, so we do not expect it to be co-located with a GM130 marker, and indeed that's what we see. So coming back to that slide, we have this. We don't have co-location of the RAB8 and the G130. The RAB9 though is located with the lyso tracker, RAB11 with transferrin. And the beauty of BRET again is the real-time nature, so we can actually track these different markers through the different compartments. So we have KRAS as plasma membrane. As the receptor is activated, it is internalized and comes off the membrane. See that in panel A, and then it goes through different compartments. So it goes through the RAB5 compartment in D first, then followed by RAB4 compartment, which is shown in C, and then it will start going into later compartments. So the RAB7 compartment, and later on RAB11. And meanwhile, you have increased signal from the endoplasmic reticulum with the RAB1. Interestingly, we don't see a change in signal with RAB8 and RAB6, and this may be reflecting a steady state situation, so there's no net change in that particular compartment. So now I'd like to move on to heteromerization and a novel approach to studying these complexes. Firstly, the definition of receptor heteromerization. This was decided by a group that met and then published subsequently in Nature Chemical Biology. And the definition agreed was that a receptor heteromer is a macromolecular complex composed of at least two functional receptor units with biochemical properties that are demonstrably different from those of its individual components. So this is a large complex, illustrated here in a very simple way by two receptors, but there are likely to be multiple other proteins involved. The minimal unit for it to be a heteromer, there should be two functional receptor units there. And as a consequence of there being two receptors, there is some kind of allosteric modulation which results in different biochemical properties compared to if those receptors were expressed individually. There could be direct receptor interactions, but there could just as easily be other proteins in between the receptors, and those proteins could be at the level of the membrane. It could be another receptor, or it could be adapted proteins across, for example, intracellularly. But the idea is there is some way that allosteric modulation can be transferred from one receptor to another in this complex. So what are the implications for this? If we have a GPCR in isolation in the membrane, we screen compounds against that. A particular compound is likely to have a particular effect, so compound A would have effect A. However, if there are heteromer complexes forming, there could be allosteric modulation occurring between these, and a particular ligand A could still have its effect A, but it could also transactivate GPCRB and have a different effect, or indeed have a completely different effect AB, showing different pharmacology altogether. So now we have a situation where we're going from this concept of a GPCR signal, so a particular GPCR that is interacting with a certain G protein. So we used to talk about angiotensin receptor as being a GQ-coupled receptor, but now we talk more about profiles. We talk more about a GPCR interacting through potentially multiple different G proteins, and also potentially through arrestin as well. So we now have this concept of biosignaling, where potentially a ligand could be interacting with the receptor and giving a different signaling profile compared to a different ligand binding the same receptor. Now this process and this concept extends to heteromerization. And because of this change in pharmacology due to allosteric modulation, we could have different coupling to G proteins and different coupling to arrestins. So this is still biosignaling, but it is as a consequence of heteromerization. So we've considered this and tried to come up with a way of actually interrogating these particular complexes in a way that gives us ligand dependency. So we've taken a receptor A, we've added a first reporter component, so this could be a donor for BRET, for example, and then we've taken the second receptor, receptor B, and we haven't labeled it, but instead we've put the second reporter component onto an interacting group. So the first and second reporter components are two components of a proximity-based system. They could be BRET, but this could also be FRET, or the enzyme fragment commentation system, or the TANGO system, or a split luciferase or a split fluorophore system. So any system which gives you a proximity readout when you have two reporter components coming into close proximity. And the idea is that when a ligand binds to the receptor B, you get activation. The interacting group here is translocated and interacts, or a conformational change occurs, changing the interaction with the receptor complex, and as a consequence you get a change in proximity of the first and second reporter components that then gives you a readout that you can measure. This is the particular configuration for intracellular signaling, but we can also just as easily flip it over the other way, so that the first reporting component is now extracellular, the second reporter component is attached to a ligand, so this is essentially a fluorescently labeled ligand, and now our ligand, which is not labeled, is competing off this interacting group, or this fluorescently labeled ligand, and as a consequence we have a heteromer selective competition assay. So it's exactly the same concept, but in terms of binding. So to illustrate this for BRET, we have our receptor A with a luciferase, our receptor B untagged, our YFP attached to arrestin. The ligand binds selectively for the receptor B, or the heteromer, and as a consequence we get a ligand-induced BRET signal from this particular conformation. Now in a cell situation you will get all sorts of different complexes. At a simplistic level, if there's just the two receptors, you will also get receptor A homomers, but these will not give you a signal because the ligand binding, or the ligand doesn't bind, and therefore we don't have acceptor translocating and interacting. In contrast, receptor B homers will activate on addition of the ligand, but even though they're recruiting the acceptor, there's no donor present and therefore no signal. So these two homomers are kept in the dark, and we have this selective signal from the heteromer complex. Here I've just put up the front cover of Assay and Drug Development Technologies and a list of original articles and reviews and book chapters that we've published using and describing receptor hit. This is an illustration where receptor hit has been used to look at GI coupling. So this is the CCR2-AT1 heteromer. Here we have the change in BRET signal induced by the CCL2, and you can see this increase, this increased change in BRET signal. It's actually a decrease, but I've shown as an increase here for simplicity. We have this change that is ligand dependent and dose dependent, and in the absence of angiotensin receptor, the addition of Ang2 doesn't make any difference, and you can see this flat line across the top where you have CCL2 at maximal dose and then Ang2 as a change in doses. Down in D, however, we have the AT1 receptor present. So now if you have G alpha I R-Luc8 and CCR2 YFP, you again see this dose-dependent increase in BRET when we have the CCL2 added, and again this is a change in BRET signal, but we see the opposite happening. If CCL2 is present at 100 nanomolar, and then we're adding the Ang2 in a dose-dependent manner, we see this inhibition of that signal. So this implies that the activation of the angiotensin receptor is somehow inhibiting the function of the CCR2 receptor. We can then see the receptor hit with the arrestin, and again similar conformation as we described before. Here we have the presence of AT1, and we have this heteromer complex. So if we look at that in terms of the readout, we have this arrestin recruitment to CCR2, but in the presence of AT1, the addition of Ang2 gives us this increase in BRET signal, but the addition of both Ang2 and CCL2 in combination gives us a much larger signal. And to come full circle and tie in the trafficking with the heteromer concept, here we have an illustration where we have the AT1 receptor with alucate, and we can see the internalization away from the plasma membrane, where we have less proximity to the KRAS tagged with Venus, and then we have trafficking to the RAB5, RAB7 and RAB11 compartments. And then if we then show the AT2 receptor, again tagged with alucate, we see no internalization, and this is to be expected from the literature. But the interesting thing is if we have the AT2 still labeled, but this time introducing AT1, if the AT1 is not having any effect at all, then we would expect to still see no effect of ligand-induced, no ligand-induced internalization or translocation into different compartments. But actually, and interestingly, we see this increase in signal at the plasma membrane. So we actually have the opposite effect. We have an increase in alucate AT1 at the membrane due to the presence of the AT1 receptor. Now, our working hypothesis for this is that we have internalization of the AT1, and then we have more trafficking of the AT1-AT2 complex up to the membrane, and therefore this increase in the AT1-AT2 complex, and therefore more alucate at the plasma membrane in proximity to the KRAS Venus. So now I'd like to move on to the BRET ligand binding assay, and this is work we've published recently in Nature Methods, and this is a fantastic collaboration with Promega and BMG and the University of Nottingham. And here we have, just to illustrate this, we have the nanoluke having a BRET signal across to the fluorescent ligand, which is bound to the GPCR, and that's competed off with unlabeled ligand. So here we have the nanobret, here we have alucate on the N-terminus of the beta-2 adrenergic receptor, and we're not seeing any signal here. But if we have instead the nanoluke on the N-terminus, we're actually now seeing a nice specific dose-dependent signal. And this is, we have a signal peptide that is enabling that expression of the nanoluke on the N-terminus. Here you can see it with the BY630 fluorophore and comparing that with the BYFL fluorophore. And you can see there is similar pharmacology, but the difference is that the BY630 is much more redshifted, and therefore we have very little background, whereas the BYFL is not so redshifted, and therefore we have this increased overlap between spectra, and therefore this higher background. And this is just illustrated here. So if we do actually have the 0 on the bottom here, and you can see, even though it's similar pharmacology, we have this much lower background with the BY630, illustrating why it's a good idea to go to red in these situations if you can. And this illustrates here a couple of aspects of the nanoluke compared to alucate. Firstly, we have this slight shift to the blue, which gives us better signal separation, or spectral separation. But more importantly, this is illustrated in terms of the luminescence on the right-hand side. So here we have the nanoluke signal being much higher than the alucate signal, and in this particular assay it was about 70-fold. So we're looking at a much stronger signal, and this means that even though we are losing signal or losing donor signal down as we come towards the 600 wavelength, it's still appreciably higher than alucate, which means that we can then transfer energy across to these red fluorophores. It's unclear why the nanoluke is better than alucate, although a working hypothesis is that it is to do with expression and the ability of the N-luke to actually be expressed and folded properly on the N-terminus. And this may be part of its evolution. The nanonucleus is evolved to be squirted out by these shrimp in the deep sea, and it's probably evolved to be able to exist and configure appropriately in the external environment, whereas the arleucate is intracellular and therefore perhaps not quite so happy outside the cell. You can see here the saturation binding, so very nice binding curves here with very low background, and there are many orders of magnitude here that simply wouldn't be able to be generated with radioligand binding. So some very nice pharmacology here, and we illustrate here with the panel C, and this is work from the University of Nottingham from my collaborator Stephen Hill and Lee Stoddard. Here we have the background with the A1 receptor, and that is giving us a nice negative control. And we have here, again, appropriate pharmacology of these different ligands for the adenosine receptors A1 and A3, and this works nicely as well for an agonist as well as antagonist, and that is illustrated down the bottom here with the ABEA compound. And the wonderful thing again about BRET is that it's very good for real time, and this is also the case for binding. So here we have real-time assays, and this kind of approach gives you similar KDs compared to the saturation experiments. And finally, interestingly, the A1 receptor and the A3 receptor, using different fluorophores, there's not a lot of difference with the A1, but there is a difference with A3, and this may actually reflect some cooperativity in the complex, potentially with homerization. So illustrating this now with the angiotensin II, so also works very nicely with peptides, the Tetramerization Ang2, and we can see with various different ligands, both antagonists and agonists, you can see some nice pharmacology here. So just illustrating this, we have the Tetramerization Ang2 ligand and the BRET signal coming across from the nanonucleus, and as we increase the concentration of olmesartan, this is competed off, and you can actually see this nicely on the left-hand side with the figure. As you increase the dose of olmesartan, we're now seeing the competition, and this was all done with Ferrostar. Now with the PD123319, this molecule actually is selected for AT2 receptor, so we don't expect it to compete off the Tetramerization Ang2, and in fact that's what we see here, so we don't see the competition. Now in terms of the receptor hit, again as I mentioned before, it can be carried out with ligand binding as well. And so we have the nanonucleus giving us a BRET signal with the TAMRA, but now the TAMRA is actually bound to the angiotensin II type 2 receptor because we have a maximal dose of olmesartan blocking it binding to the AT1. And if you then add the PD compound, this competes off the Tetramerization Ang2, and so that again shows selectivity for the AT2 receptor. And you can see that here. So we have 1 micromolar olmesartan blocking the AT1 receptor. So this competition with the PD123319 is due to the competing off of the Tetramerization Ang2 from the AT2 receptor. And then finally, just as an additional control, here we have the AT1 and the AT2 receptors. We have the AT1-AT2 heteromer combination, and then comparing that to the AT2 receptor combination alone. And of course, we're interested to see if we have a similar potency, and indeed we do. So we have no significant difference between having binding to the AT1/AT2 heteromer versus binding to the AT2 receptor and displacement with this PD 123319. So with that, I'd like to acknowledge the people that did the work, current and selected people from my lab from the past, and indeed a whole range of collaborators both in industry and in academia, and of course all my funding bodies, and I'd be very welcome to answer questions at the end, but now I'd like to hand over to Carl. Thank you very much.
Thanks, Kevin. To conclude this webinar, I will spend a little time telling you about a couple of microplate readers that we think will help you in detecting your BRET assays. As we have seen today, the BRET system, while extremely useful for a wide variety of applications, it is also associated with a number of challenges. The low signal makes sensitive detection important, which in turn means that selecting the optimal wavelength is important. This wavelength optimization needs to be done for a variety of donors and acceptors that may be used in your particular BRET assay. Because of the challenges that are involved in detecting BRET, it is desirable to collect as much light as possible, making filter-based instruments preferred. Typically, monochromator-based instruments perform poorly, as seen in the panel on the right. However, the Clariostar has been found to be the sole monochromator-based plate reader suitable for this challenging assay. I will focus my portion of the webinar on the Clariostar and the Ferrostar FSX, the two BMG readers that were employed to collect the data shown today. In general, the Clariostar is used for assay development, while the Ferrostar FSX has a number of advantages that make it an excellent choice for high-throughput screening. Although our focus today is on BRET assays, both readers exhibit excellent performance in the multiple modes shown here. Both readers lead the way in sensitivity as measured by limit of detection. This extends to bottom reading, where a true, direct, free air optical path allows for outstanding sensitivity in all modes. And switching between top and bottom reading is controlled in the software with ease. No need for additional hardware installation to enable bottom reading. The key attribute of the Clariostar is a monochromator based on linear variable filters. In essence, this system allows you to create filters within the instrument that have the wavelength of your choosing with a bandpass up to 100 nanometers. For fluorescence experiments, the appropriate wavelength for excitation and emission of your fluorophore can be selected, and an adjustable dichroic assures that all characteristics are optimized for performance in your assay. For BRET experiments, multiple emission wavelengths can be selected, and the ability to select wide band passes is especially useful for sensitive detection of the lumiphores with broad emissions in these experiments. By implementing LVF technology in a plate reader and combining it with the best possible light handling, there is a significant improvement in the amount of light lost by the Clariostar. This is depicted graphically in the top figure. The bottom figure gives you an idea of the benefit that can be derived from being able to adjust to any wavelength and bandpass. The LVF monochromator lets you choose the best possible wavelength and bandpass for your experiments. The high performance enabled by the LVF monochromator, along with the excellent dynamic range in luminescence, all contribute to the Clariostar's ability to detect BRET assays when other monochromator-based readers cannot. Further utility is provided by the spectral scanning capabilities. An example of this is shown in the lower panel. Based on these spectral scans, you can begin to make choices about what monochromator settings you will need to have success. Because of its excellent sensitivity, assays developed on the Clariostar will easily translate to the Ferrostar FSX. The Ferristar line has been the gold standard for high-throughput screening, and the FSX moves the bar even higher with improvements in speed and sensitivity. The FSX includes the best possible hardware components for all assays. These components are depicted on the right. From dedicated light sources to truly matched PMTs, and finally, assay-specific modules, the FSX has what you need to be sure that assay performance is optimal. This includes the ability to detect 2 emission signals in a simultaneous fashion. This is advantageous for any assay where 2 signals are produced because it not only cuts down on read time, but also reduces the possibility of variation in results that could negatively impact your analysis. The Ferristar FSX has performance parameters that are identical to the Clariostar and Luminescence, and we have used what we have learned from spectral scans to optimize the optic modules used to detect BRET assays. These features, combined with the simultaneous dual emission detection capability, enable high throughput when using the FSX. The excellent performance of the FSX in BRET assays is well established, as you have seen already. And we hope that if you are planning to use BRET, regardless of throughput, you will consider BMG LabTech to provide a reader with the excellent sensitivity that you need. Thank you for taking the time to join us today, and we will now be happy to answer any questions.
Okay, I'd like to thank you all the panelists for their interesting contributions there. We've got plenty of questions, but not an awful lot of time, so we'll run through them as soon as we can. And if I could ask our speakers to keep the answers brief, would be great. Okay, so the first one, unfortunately Thomas isn't with us this afternoon for the questions and answers. He couldn't make it, so the first one is to Kevin. But I'm sure that Carl would like to answer this one. And the question is about it's on the kinetic side of the measurements there. And basically, can the kinetic measurements be read on a full 384 well plate on a Ferristar? And if so, is each well sampled multiple times over the plate time course?
I can answer that if you like, Robert. So it's Kevin here. So the answer is yes. I'm getting too much feedback on the phone here, but we have run with the Ferristar, and you can do 384, and you can run a full plate, and what you do is you read each well through both wavelength channels, and then go on to the next well, read that, and go round, and then you can go back and start again from the first well. So absolutely.
Okay, this one is once again for you, Kevin. This one is, and it is basically, you were saying how good, well, both you and Thomas were saying how good BRET is at detecting even the smallest changes. Could you give the guy who asked the question an estimate for the smallest distance change that could result in a significant BRET signal change?
Yes, absolutely. So, and in fact, I believe this is, yeah, absolutely. So we have published a paper on this, and I'm happy to forward that paper on to the person who asked the question. And the answer is, BRET, the distance change happens very rapidly. So between about 2.5 nanometers and, this is for R-Lucate and Venus combination, between about 2.5 nanometers and about 7.5 nanometers, there's a rapid change. So if it's less than 2.5 nanometers, you won't see much difference. If it's more than 7.5, you won't see much difference. But it's anywhere in between that range, you'll see a dramatic change.
Okay, excellent. So one more question. If antibody receptor binding was studied, does this distinguish the false degraded antibody from the unstressed antibody? And do you see the difference in the receptor binding?
Okay, that's an interesting one. And again, I'm happy to liaise with the person who asked that question offline. We haven't done an awful lot of work with antibodies. So to be honest, I'm not quite sure of the question.
Well, I think we can certainly put you in touch with each other. All right, one more last question. Yep. For the BRET ligand binding assay, how do the IC50s compare to traditional radioligand displacement assays?
Yeah, they compare favorably, absolutely.
Good, excellent. All right, look, ladies and gentlemen, unfortunately we've run out of time. I'd like to go through more of your questions with the panel, but obviously they will see the questions and hopefully we can be in touch with each other and follow through on this one. Please remember that the webinar will be stored on our website, that's ddw-online.com, and so you can get that on demand if you want to catch up with the webinar later on. So once again, a big thank you to our speakers, a thank you to our sponsors, BMG, LabTech, and Promega, and I also thank you, our attendees, and hope that we'll see you again for another Drug Discovery World webinar. Thank you very much, and goodbye.